All right. So way back in the late 1830s, a German physicist by the name of George Simon Ohm started doing some experiments. And I'm going to draw kind of a picture of the experiment that he did. Okay. So he had a material or device under test. So I'm going to represent that like a big black box over here. I'm just going to call this material under test. And he hooked some electrical terminals up to these materials, like so, forming a two-terminal network. And then he electrically excited this network. Now, I am going to intentionally leave it ambiguous as to whether or not he used a voltage supply or a current supply to do this. A, because it's a really, really old experiment, and his version of an electrical excitation force would vary so differently from what we would think to use of an electrical excitation force in a laboratory setting that is really not an analogous thing. And B, because it literally doesn't matter. Okay. So what he did when he electrically excited this material is he measured the voltage drop across the material under the test, which I'm going to call V test like so. And he measured the current flowing into the terminals of the material under test. And I'm going to call that current I test like so. So does this experimental setup look like anything that you guys have seen? I would argue it's the exact lab we did on Friday. We had a simple material. In that case, it was a resistor. You measured both the voltage drop across and the current flowing through the network. So for those of you that completed the lab assignment sheet and all of that kind of good stuff, what was the units of the slope of that line? So what was the x-axis? Let's start there. And what was the y-axis? So if you set things up correctly, you probably had, or should have had, voltage measured in volts on the x-axis and current measured in milliamps on the y-axis. And when you plotted your data, you should have gotten roughly, I want that to be a different color, a straight line. So as this is currently written, this slope, rise over run, would be in milliamps per volt or 10 to the minus 3 amps per volt, okay? So the important part of this, what I made you guys do and what George Simon Ohm did, is he found out that current and voltage were proportional, okay? That's why we get a straight line for our graph. And he called this constant of proportionality the resistance. Okay? So we're going to say that our resistance R is simply the ratio of the voltage drop across the terminals of our network divided by the current flowing into the terminals of our network. I want to make a note here. I've defined these quantities in such a way that the current is flowing into the positive polarity terminal of the material under test so that this material under test is absorbing power from the source that is exciting it, okay? We'll talk about that more in just a couple of moments, okay? So from this relationship, we can see that the units of resistance, which are typically called ohms. So we're going to say that 1 ohm, symbol capital omega, is going to be just 1 volt per 1 ampere. And the thing that you guys actually calculated, the slope of the line where we have current over voltage, is another quantity that we might be interested in. It's just a slightly different way of representing that same proportionality constant between current and voltage in a network. We're going to call that the conductance, where conductance has a symbol capital G. It is just the ratio of current over voltage, and this is going to have a unit of a Siemen, Siemen. Symbol is capital S, so this is named after a different German scientist. This guy started the Siemens Electronics Company. And this is an amp per volt, so that we could really say that this slope here was measured in millisiemens if we wanted to. Now, it should be fairly obvious that since resistance is simply the ratio of voltage over current, and conductance is the ratio of current over voltage, that these guys are reciprocals of each other. So I can say that my resistance is equal to 1 over my conductance, or I can say that my conductance is simply 1 over my resistance. So other than today, we're really not going to deal with conductances at all in this class, okay? So I would highly encourage you guys that whenever you're given a conductance, like in your homework sets for today, maybe the ICA for today, although it's not particularly necessary, you simply just take the reciprocal of it so that you can treat it like a resistor, because you know loosely how resistors behave, and we'll get into more of that in a little bit, and then just go on about your day. If you want to treat it like a conductance, technically we have to learn a bunch of special rules on how to treat that, and there's really not any point of it when it's actually easier to just take the reciprocal of it, treat it like a resistor, and go on about our business. Okay. So I want to define resistance and conductance for you all. So we're going to say that resistance is a measure of how difficult it is to pass current through a circuit element, meaning that the larger the value of the resistance, the harder it is to pass some fixed amount of current through it. And transversely, conductance is just going to be a measure of how easy it is to pass current through a circuit element. Okay. So before we do anything else, I want to put Ohm's law in the form that you guys are probably a little bit more familiar with, and then we're going to play around with some things as well. Okay. So in order to facilitate this, I'm going to introduce you guys to the schematic symbol for a resistor, which you should hopefully all already know. So here's my schematic symbol. And I'm just going to represent the resistance of this element right now with the letter R. Okay. So in this particular case, let's define the positive polarity terminal of this resistor on the left, the negative polarity terminal on right. And so this is going to be the voltage drop across our resistor VR. And this is going to be the magnitude and direction of the current flowing through the resistor IR. Okay? So whenever we have current flowing into the positive polarity terminal, like we have here, what we're going to find is that the voltage drop across our resistor VR is simply the current flowing through our resistor times the resistor value itself. Okay? This is the Ohm's law that you guys learned back in Engineering 120 and have been using in various forms in your other courses. Okay. Now, where things get slightly more complicated, and it is very slight, is that if I have a resistor and I have the voltage defined with the opposite polarity, so that the current is flowing into the negative polarity terminal, we're actually going to have to include a negative sign in our equation for Ohm's law. So the easiest way to remember this is if current flows into the plus sign, Ohm's law gets a plus sign. If current flows into the minus sign, Ohm's law gets a minus sign. It's not particularly difficult. Okay. Let's talk about the reason why we have to do this. So a resistor, what does it do fundamentally? Let's start there. Okay. What was that? Turns current into heat. Okay. So it converts electrical energy into thermal energy, but that's just a little bit more formal way of saying exactly what Matthew just said. Okay. All a resistor can ever do is convert electrical energy into heat. Okay. So it provides a resistive path, giving electrons a place to bounce off of, which limits current flow. And those physical interactions between those electrons and the atom inside of the resistive material generate heat. So as you strike those atoms more and more, they vibrate, causing heat to happen. Okay? So a resistor cannot store any energy whatsoever. So it always has to be absorbing power and absorbing energy. So this second equation here, where we have current flowing into the negative polarity terminal, takes that into account because essentially one of those quantities, either IR or VR, must be a negative thing because the resistor is literally incapable of ever storing any energy. Okay. So this is just our way of taking care of the fact that we need to obey how a resistor behaves in real life. Okay, so just to recap again very briefly, the current's flowing into the plus terminal, give Ohm's law a plus sign. The current's flowing into the minus terminal, give Ohm's law a minus sign. Not particularly difficult. Okay. All right, so I want to explore a couple of things related to resistance really quickly. Okay, so resistance as a material quantity is related to not only the material that is being used, but also its physical structure or geometry. Okay. So it's been a really long time since I've taught Engineering 121. But back when I taught it, we were introduced to the following relationship, where resistance R could be defined as resistivity. So that's rho sub E times length over cross-sectional area, right? Where rho sub E is the material contribution to the resistance, and the length and area are the geometric contributions to the resistance, okay? So if we just have a lump piece of material and we wanted to know what resistance is exhibited, this is the equation that we would use. So I want us to take a moment and figure out what the resistance of a long piece of wire is, because we've been making an assumption in all of our previous classes that we can treat wires as if they are a short circuit, meaning that they have no resistance. And I want to explain why we get to do that, okay? So let's say that I have a very long section of wire, All right. So here's my long section of wire, and for what it's worth, I'm going to say that current is flowing down this long section of wire longitudinally because the direction absolutely matters. I could, if I wanted to, be a huge jackass and say that current is flowing in from the top and out from the bottom, and that wire would exhibit a different resistance. Doesn't really tend to work that way, but I could do that if I were so inclined, okay? So let's say that the material that this wire is made up of is copper. I'm going to take my phone out really quickly because I can't ever remember exactly what the resistivity of copper is. I feel like it's something 6.8 times 10 to the minus 6 or something, but I could be just completely wrong there. Phone's being slow. Yep, totally wrong. 1.72 times 10 to the minus 8 ohm meters. Okay. And I'm going to say that this is an AWG number 22 copper wire. Okay. The reason I'm using AWG or American wire gauge number 22 copper wire in this example is because that's literally the wire that you guys used in your jumper kits in your previous classes. It's the same size of wire that we're going to use for connecting things in this class. Okay. So it's representative of the wire that we're used to use. I'm going to look up on my phone what the diameter of solid core AWG number 22 wire is. And it is 0.0253. I believe that is measured in inches, but let me just double check the units on this table. Let's put it in millimeters, that'll be easier. So the diameter is 0.644 millimeters. And let's say that we're dealing with a total length L is equal to 1 meter. Okay. Now, before we move forward in our calculation here, I want to ask you guys a question. How long is 1 meter compared to the length of the wires that you've used to connect things in circuits previously? Significantly longer, right? A meter, if I'm remembering correctly, is a little bit longer than a yard. So typically speaking, you guys might have used, 10, maybe 20 centimeters of wire at the absolute longest. So this is probably at least 10 times longer than any length of wire that you've ever connected anything with. Okay. So I want us to plug in these parameters and figure out what the resistance of this 1 meter long section of AWG number 22 copper wire is. Okay. So for this particular example, we would have the resistance of our wire is the resistivity. So that's 1.72 times 10 to the minus 8 ohm meters times our length of 1 meter divided by our cross-sectional area. Since we were given diameter, I'm going to have to do pi over 4 times the diameter squared. So pi over 4 times our diameter of 0.644 millimeters squared. And to handle the unit conversion there, I'm going to say that 1 meter is 1,000 millimeters, and I need to square that conversion factor as well, so that the only thing that survives when I cancel all of these units out is the ohms in the numerator, right? So throwing this into my calculator, 1.72 times 10 to the minus 8 over pi over 4 times 0.644 squared times 1 over 1,000, also squared. I got 0.05280 and some change ohms, or 52.804 milliohms. So a 1 meter long section of copper wire has a resistance of about 50 milliohms. What's the smallest resistor that you guys used in your 120 series? It's the one that made the LED most bright. 220. So a 220 ohm resistor is the smallest one that you guys use. The largest ones were probably 10 kilo ohm or 20 kilo ohm resistors when you were setting up your single-ended ratiometric measure, your voltage divider network. Sorry for getting fancy there. Okay. So how does 200 ohms compare to this? Well, let me just do 200, or actually 220, divided by answer. It's 4,000 times larger. So if the smallest resistor that we've ever used is 4,000 times larger than the resistance of a 1 meter long section of wire, which is 10 times longer than any wire that we've ever used, this is a pretty good reason to why we get to assume that wires have no resistance. It's not unless we're dealing with essentially what are called current measuring resistors and things like that, which are resistors designed to have extremely small resistances comparable to this, that we actually have to start caring about the resistance of a wire or anything like that. Okay. So we will continue to assume that wires have no resistance for this class as well, but at least now we know why we're doing it. All right, so does anybody have any questions, comments, or concerns about what we've covered thus far? Not the last thing that I want to touch on very briefly is just the power absorbed by a resistor, which is just going to use Ohm's law and the power relationship that we came up with in our last class meeting. Okay. So the power absorbed by a resistor, I'm just going to label that P sub R, is going to be the voltage drop across the resistor times the current flowing through the resistor. P is equal to V times I, just like we dealt with in our last class meeting. Using Ohm's law, I can say that the current flowing through my resistor is just V over R. So I could rewrite this as the voltage drop across my resistor squared divided by my resistor value itself. Or I could write it as the current flowing through my resistor squared multiplied by my resistor value. So these are three different ways that we can calculate the power absorbed by a resistor. It should always be a positive quantity. So it doesn't matter if we get the sign on the voltage correct or not. V squared is going to be positive over a positive resistor value. Same thing, doesn't matter if we get the current direction correct. Even if we have a negative current, I squared is going to be a positive quantity, multiplied by R is also going to be positive. So our resistors will always absorb power. If we're dealing with conductances, it's going to be practically the same relationships, except that we just need to swap I and V, sorry. So the power absorbed by a conductance is still going to be the voltage drop across the conductance multiplied by the current flowing through the conductance. So this is going to look like Vg squared times G, or Ig squared over G. So now let's talk about Kirchhoff's voltage law. So Kirchhoff's voltage law states that, let's write this down. So Kirchhoff's voltage law, or KVL, says that the sum of the voltage drops around any closed path. So in this case, closed path means we start and end at the same node. So I'm just going to make a little note here. Must equal to 0. So let's talk very briefly about why that is. So what is a voltage again? Go to your notes from our last class meeting. Difference in potential, okay. What's the other definition? We talked about two different definitions. The second one I gave you was difference in electric potential between 2 points in a circuit. What was the first one? Work per unit charge, okay? So work or energy per unit charge means that anytime that we see a voltage, there has been energy transferred, okay? So if we sum up all of the transferred energy around our closed path per unit charge, that is just us applying the law of conservation of energy to our system. So that's why Kirchhoff's voltage law must always be satisfied. So both Kirchhoff's voltage law and Teligens's theorem are essentially the law of conservation of energy applied to circuits. Okay. So KVL can be used to determine the value of any unknown voltages in our system if we know what the other voltages are, and we can use it in combination with Ohm's law to also find out currents that are occurring in our system. So let's start with something ridiculously easy, okay? So this is more of a way for me to show you how I choose to apply Kirchhoff's voltage law and how I highly suggest you guys do it as well. So let's start with a 9-volt battery. Five-volt battery, some arbitrary resistor R. And let's make that a 3-volt source there. I'm going to let you guys choose what the polarity of that resistance, the polarity of voltage drop across that resistance is. So do you want positive polarity on the left or positive polarity on the right atom? On the left. Positive polarity on the left, okay? So this is the voltage VR that we are looking for. So when I apply Kirchhoff's voltage law, I tend to start defining my path in the bottom left-hand corner. And then I either go clockwise or counterclockwise. It doesn't really matter which direction. We're going to wind up doing both here in a moment, just to illustrate that it doesn't matter. We're going to get the same result either way. So I'm going to start by doing KVL in a clockwise path. Okay. So I'm going to start here, and then I'm just going to go up and around in a clockwise direction, like so. So I'm just going to write here KVL clockwise. And so here's how I write my equation. If I see the negative polarity terminal of a voltage first, I give that voltage a minus sign. If I see the positive polarity terminal of the voltage first, I give it a plus sign. It's that simple. Okay? So if I'm starting at the bottom left corner and I'm going up, the first thing I see is the negative polarity terminal of that 9-volt source. So I'm going to write that as negative 9 volts. Then I see the negative polarity terminal of that 5-volt battery. So I'm going to do minus 5 volts. Then I see the positive polarity terminal of the voltage VR. Then the positive polarity terminal of the 3-volt source. And now I'm back at the same node that I started from. So I just set it all equal to 0. And then I can rearrange this guy. So I'm going to keep that VR on the left-hand side of the equal sign, and I'm just going to move everything else over, right? So negative 9 volts moved to the right-hand side of the equal sign looks like positive 9 volts. Negative 5 volts moved to the right-hand side looks like positive 5 volts. Positive 3 volts moved to the right-hand side looks like negative 3 volts. 9 plus 5 is 14, minus 3 is 11 volts. So according to Kirchhoff's voltage law applied in a clockwise direction, VR is equal to 11 volts. Now, just for the hell of it, let's do KVL in the opposite direction. So counterclockwise. The first thing I see is the negative polarity terminal of the 3-volt source. So I'm going to see minus 3 volts, then minus VR, then plus 5 volts, then plus 9 volts. And now I'm back at the bottom left-hand corner. So I set it equal to 0. Now I'm going to move VR to its own side of the equal sign. So here's VR by itself. Essentially treat it like I had moved it to the right-hand side, and I'm just going to leave everything else the same. So that's going to look like minus 3 plus 5 plus 9. So minus 3 plus 5 is positive 2. Positive 2 plus 9 is, once again, positive 11 volts. So it doesn't matter which direction we choose, we're going to get the same result. If I or Adam had chosen the opposite polarity, what would have happened to the voltage? It'll just introduce a negative sign. Yep, that's it. So this is simple application of Kirchhoff's voltage law. Very, very boring. Okay. So let's get into a little bit more complicated thing. So here I've got a 15-volt source. Here I've got a 10-ohm resistor. Here's a 20-ohm resistor. I'm going to throw a dependent source into the mix. So let's make this twice Vx. Let's make this one a 30 ohm resistor. This one a 40 ohm resistor. And I'm going to define Vx to be the voltage drop between these 2 points in the circuit. Some of you may be hesitant or struggling to understand what that Vx in the middle of the circuit there means. It's just like if I had applied a multimeter between 2 points and I was trying to measure that voltage Vx. And that particular voltage happens to control that dependent voltage source on the right-hand side of my circuit, right? So as long as I'm just measuring the potential difference between any 2 points in my circuit, it is absolutely fair game for me to call that a voltage. Doesn't matter if it's across an element or just between 2 points, still fair game. All right, so this is an example of what's called a single loop circuit, where all of the elements are connected together in series. Okay, so we can see that the 15-volt source is in series with the 10 ohm resistor and the 30 ohm resistor. The 10 ohm resistor is in series with the 20 ohm resistor and the 15-volt source, and so on and so forth. But based on our early definition of a series connection, we can see that we only have series connections in this system. Okay. So whenever I see a single loop circuit like this, my first step is almost always to apply Kirchhoff's voltage law. Okay? But we have a little bit of a problem here, inasmuch as the voltage drop across our resistors has not been defined. So I'm going to take a moment to do that now. I'm going to be very, I'm probably going to put too much information on here based on most of you guys' level of comfort. Over time, we're not going to have to get so granular about these things, but I just want to make sure that everybody can follow all of the steps that I'm doing here, okay? So I'm just arbitrarily going to assign the voltage drops across all of these resistors. So let's say that this voltage is V10, positive polarity on the left. This voltage is going to be V20, positive polarity on the left. This voltage will be V30, positive polarity on the left, and this voltage will be V40, positive polarity on the left. Now we're going to do one other thing here. And I'm kind of getting a little bit ahead of myself, but I know that since not all of my resistances have defined voltage drops, I'm going to need a current somewhere. Yes.
Bottom left resistor 20 ohm.
30. So top left 10, top right 20, bottom left 30, bottom right 40. And then for their labels, it's just V and then the size of the resistor. Okay. So I'm arbitrarily going to say, just based on how I prefer to do Kirchhoff's voltage law, which is clockwise, that there is some common current I flowing clockwise around this circuit. And now I'm going to apply KVL. So I have a few different paths that I could apply KVL to here. So let's explore some things, right? So I think that I could do KVL around this path. I could do KVL around this path, or I could do KVL around this path. Those are all closed paths, starting and ending at the same point. Okay. So which one would you guys like to do first? Green, blue, or purple? Green. Okay. So KVL around our green path to me would look like negative 15 volts plus V10 plus Vx minus V30 is equal to 0. So right now I have one equation and 3 unknown quantities. So what I'm going to do is I'm going to use Ohm's law to get rid of some of those unknown quantities, or to put some of those unknown quantities in terms of something that's going to pop up numerous times. I mentioned earlier that because all of these elements are in series, they're all going to have the same current flowing through them. So what I'm going to do is I'm going to use Ohm's law to get rid of some of those variables, because that will allow me to put at least all of the resistor voltage drops in terms of a common current I, instead of treating them as individual voltages, okay? So over here on the right-hand side, I'm going to write some Ohm's law equations. So let's start with that 10 ohm resistor. So using Ohm's law, the voltage drop across the 10 ohm resistor should be what? And I'm looking for it in terms of that current I. I times 10 ohms, okay? So that seems reasonable. What about for the 20 ohm resistor? I times 20, okay? What about for the 30 ohm resistor? You're wrong. Why are you wrong, Adam? Negative, because the current is flowing into the negative polarity terminal. So negative I times 30 ohms. And for the exact same reason, V40 is negative I times 40 ohms, right? I define that current I, which I don't know what direction it actually has, nor do I care. But I defined it as if it's flowing in a clockwise fashion, which means it's flowing into the positive polarity terminal of the 10 ohm resistor, into the positive polarity terminal of the 20, into the negative of the 40, and into the negative of the 30. So I need to make sure that my Ohm's law has a negative sign there, okay? All right, so I can take what I need from those Ohm's law relationships and move them into that KVL equation and kind of reorganize things really quickly. So let me go back to green here. So I'm going to move the 15 volts, the constant term, to the right-hand side of my equal sign, okay? And so I'm only going to have variables on the left-hand side. So V10 is just I times 10 ohms. So I'm going to have I times 10 ohms. Vx, can't really do anything with that. Now I'm going to have minus V30, so that's going to be minus negative I times 30 ohms. And now I'm just going to lump stuff together, right? So negative I times 30 ohms just looks like positive 30 ohms times I, and I have a 10 ohms times I, so I can add those guys together. So that would be I times 40 ohms plus Vx is equal to 15 volts. So I've gotten that first equation, or that first KVL equation that we wrote, down to, instead of one equation with 3 unknowns, it's now one equation with 2 unknowns. So it's better, but it's still not good enough. So I'm going to need to come up with another equation. Well, we have 2 other KVL paths that we could write equations for. So let's pick one of those. So blue or purple? Blue. Blue. Okay. So if we write KVL around our blue path, starting at the bottom left-hand corner, the first thing I'm going to see is the negative polarity terminal of that voltage Vx. So I'm going to have minus Vx. Then I see the positive polarity terminal of that voltage V20. Then I see the positive polarity terminal of that dependent source providing 2Vx. And then I see the negative polarity terminal of the voltage V40. And I'm now back at the node that I started from. Obviously, I can say that minus Vx plus 2Vx just looks like 1Vx, okay? And I can use Ohm's law to give me a relationship to the 20 ohm resistor and the 40 ohm resistor, both in terms of the current I. So what I'm going to do here is I'm going to leave Vx on one side of the equation. So minus Vx plus 2Vx is equal to a single Vx. Now I'm going to have minus V20. So minus V20 is going to look like minus I times 20 ohms. And then I'm going to have plus V40. So that's going to be plus negative I times 40 ohms. So there's a common factor of negative I. 20 plus 40 is 60 ohms. And so now I can see that Vx is equal to negative I times 60 ohms. Well, now I can just plug that expression for Vx into my KVL equation at green and eliminate one of those variables, right? Allowing me to solve for the other one. So let me just write this down here. KVL at green revisited. So I have I times 40 ohms plus Vx, where Vx is negative I times 60 ohms, is equal to 15 volts. So that looks like negative I times 20 ohms, or I times negative 20 ohms, however you choose to distribute your minus sign there, right, is equal to 15 volts. From this, I is 15 volts over 20 ohms with a minus sign. So that is negative 3/4 of an amp. And if I substitute in this value of I into my equation for Vx, this would come out to be positive 45 volts. So what we've done here is, well, we've increased the level of difficulty by a whole hell of a lot, I would think, even though that this circuit really only involved the use of Ohm's law and Kirchhoff's voltage law. So this was a bit more difficult than what you guys have seen. What I was trying to get out of this is expose you guys to a circuit with a dependent source where you actually have to do some work for it, which I think we've done. Bring to your attention that we can take the voltage drop across any 2 points in the circuit, which I also believe that we've done, so you'll wind up doing that later and all of that kind of good stuff. Really, the last thing that I want to do pertaining to Kirchhoff's voltage law for today is to look at a network that contains only things connected in parallel really quickly. Okay. Yes. So the last thing that we're going to deal with regarding KVL today is the following circuit. So let's say that I have a 20-volt source connected in parallel to a 10 ohm resistor and a 15 ohm resistor, like so. I'm going to say that the voltage drop across the 15 ohm resistor has positive polarity on top, like so. And the voltage drop across the 10 ohm resistor has positive polarity on bottom, like so. So we once again have a situation to where we could write three different Kirchhoff's voltage law equations. I'm not going to bother writing all three of them. I don't think it's particularly necessary to illustrate what I'm trying to show you guys here. So I'm just going to choose to write one around the left hand and then one around the whole thing. Okay. So let's start with the one around the left hand. So if I do KVL around this blue path, I'm going to have negative 20 volts minus V10 is equal to 0, which means that V10 is equal to negative 20 volts. Well, let's take a moment to look at this. How is the 20-volt source and the 10 ohm resistor, how are they electrically connected to each other? So the polarity of their voltages is opposite, but that doesn't tell me how they were connected. Are they in parallel, are they in series, or are they none of the above? They're in parallel, right? They both share the top node, they both share the bottom node, okay? So they are in parallel, but they are of opposite polarities, which means they have the same voltage, but of opposite sign. Okay? So whenever we have two elements in parallel, but their polarities are opposite, they're going to have the same voltage drop across them. We just simply need to add a negative sign. When we do KVL around the outside, which I'll do that in light purple, maybe that's the one I should have done first. I would have negative 20 volts plus V15 is equal to 0, which means that the voltage drop across the 15 ohm resistor is positive 20 volts. So once again, we have two elements that are connected in parallel, but now because they have the same polarity, they have the exact same voltage. Okay? If I were to do KVL around that right-hand mesh, right, that smaller loop there, what we'd find is that V15 and V10 have opposite polarities. So if one is 20 volts, the other is minus 20 volts, exactly what we already found, okay? So encapsulating all of that into a simple statement, elements connected in parallel with the same polarity will have the same voltage. Elements connected in parallel with opposite polarities will have the same voltage with opposite signs. Which the first statement you guys should have learned in the 120 series. The second statement is just an extension of that now that we're paying attention to what polarities actually represent. So before we move on from here, how do you all feel about Kirchhoff's voltage law? Hopefully nothing too wild or crazy, getting some thumbs up, giving some blank stares, that's okay too, I guess. You don't ask a question, I can't answer it, and I'll just go on from there. Yes.
How come you have to deal with the opposite signs in the 120 series?
So that's a very good question. You may not have realized it, but in the 120 series, every circuit that you were given, except for possibly the alligator problem, depending on how much of an ass Dr. Schwanbaum felt like at that particular day, had only a single voltage source. Okay. So whenever you have everything excited by a single voltage source, essentially all of your resistors are always just going to have the same polarity as the voltage source. So you never ran into a situation to where we had to take that into account. So like one of the things that isn't intuitively obvious, but so like I really hate the idea or the way that it was done in the 120 series where it just used delta V for everything, because you can't really explain like how do you charge a battery using that system. That's why polarity is so important, right? So if you have two voltages and they are connected to each other and they both have positive polarity on top, how do you figure out which direction current's going to flow, all of that kind of stuff. This methodology makes it okay to figure out using only deltas where you're just saying, the change of voltage is this thing, makes it effectively impossible. So did that answer your question? Good. Any other questions about this? All right, so the last thing that I want to talk to you guys about for today is Kirchhoff's current law. All right, so Kirchhoff's current law, there are three different ways that we are going to represent it, okay? But I'd first like to ask if any of you guys remember how it was explained to you back in the Engineering 120 series. Anybody just venture a blind guess? What was that, Sujita? So the total current flowing into a node is equal to the total current flowing out of a node, okay? So that is one way that we can talk about it, and that'll be our first way. So I'm going to draw a picture here to kind of explain what's going on. So I've just got an arbitrary node point here at the center. And then as part of some larger circuit, I'm going to have some wires like so. And I'm going to assign currents to each of these sections of wires. And I'm just going to kind of be lazy and have some of them pointed in and some of them pointed out. Okay. So I'm going to start with a current I1 here that's flowing in towards that central node. Let's say that I2 also flows in. I3 is going to flow out. I4 is going to flow in. And I5 is going to flow out. And then over here on the right-hand side, I'm going to write KCL number 1, because this is one of three ways that we can choose to interpret Kirchhoff's current law, okay? So this will be the one that you guys learned in the 120 series, which simply says the sum of the currents entering a node must be equal to the sum of the currents exiting the same node. Okay. So before we write a mathematical expression talking about this, let's parse through that statement, okay? So current is the rate at which charge is flowing. So if we say that the sum of the currents that are flowing into the node has to be equal to the sum of the currents that are flowing out of the node, what we're saying is that the rate that charge passes into a node is equal to the rate that charge leaves the node. This has to be true. Otherwise, we're violating the law of conservation of charge. Because if more current, or more charge flows in than flows out, we have to be destroying charge. If more charge flows out than flows in, we have to be creating charge. And both of those things are literally impossible, okay? So Kirchhoff's current law is just the circuit's form of the law of conservation of charge, okay? So if we look at this particular equation here, what I'm going to do is, or excuse me, this particular system, what I'm going to do is I'm going to write an equation. I'm going to throw an equal sign in the middle. And I'm going to say that currents flowing in are going to be on the left-hand side of the equal sign, and currents flowing out are going to be on the right-hand side of the equal sign. Okay. So I1 is flowing in towards the center, so it's going to go over here. I2 is flowing in towards the center, so it's going to go over here. And it says the sum of the currents, so I'm adding them together. I3 is flowing out, so it's going to go on the right-hand side. I4 is flowing in, so it's going to go on the left-hand side. I5 is flowing out, so it's going to go on the right-hand side. And all of my various currents are taken care of, right? So according to KCL formulation number 1, I should have I1 plus I2 plus I4 is equal to the sum of I3 plus I5. KCL successfully applied here. So now let's talk about the other two ways, very briefly, that we can think about Kirchhoff's current law. Okay. So our second formulation I'm just going to say that the sum of the currents entering a node must be equal to 0. So this does not mean that I get to arbitrarily throw away any currents that are exiting the node. Instead, what it means is that if I3 is exiting the node, then negative I3 must be entering the node. So that would look like, so I1 is entering, so it gets a plus sign. I2 is entering, so it gets a plus sign. I3 is exiting, so it gets a minus sign. I4 is entering, so it gets a plus sign. And lastly, I5 is exiting, so it gets a minus sign. So mathematically, KCL number 2 is the exact same thing as KCL number 1, except that I moved the terms from the right-hand side over to the left-hand side of the equal sign. Okay. So it's the exact same thing, both mathematically. We're just saying, hey, if it's flowing out, it's just the negative of flowing in. And then KCL number 3 is just using essentially flowing out as our positive reference direction. So we could say the sum of the currents exiting a node must be equal to 0. So in this case, everything that's flowing in is going to get a minus sign. Everything that's flowing out is going to get a plus sign. So that's going to look like negative I1 minus I2 plus I3 minus I4 plus I5 is equal to 0. which is just the exact same expression that we got for KCL number 2, except everything was multiplied by a factor of -1 because we're going in the opposite direction. That's it. So for what it's worth, you can use any of these three versions of Kirchhoff's current law, and you're going to get the correct answer as long as you apply it correctly. So if you are more comfortable with KCL number 1, then just use that. Okay. I tend to use KCL number 3 about 90% of the time, KCL number 1, the other 10% of the time, and practically never use KCL number 2. Okay. The reason why I prefer KCL number 3 is in a couple of class meetings, we're going to learn a tool called nodal analysis. And in nodal analysis, if we follow KCL number 3, all of the currents that are exiting get a plus sign. That's going to wind up giving us systems of equations that don't have a bunch of extra minus signs all over the place for me to take account of. And I know that I am particularly bad at keeping track of extra negative signs and stuff like that. So I try to put myself up in a situation where I can avoid it as much as possible. Okay? But realistically, you can use whatever you are most comfortable with. You can mix and match, all that kind of good stuff. Doesn't particularly matter. You just need to be consistent and do it correctly. So as we work out example problems here, and I encourage you guys to do this over the next few days while you get comfortable with this, make a note of which KCL version it is that you're using and which node that you're applying it at so you can make sure that you're doing it consistently. Okay. So let's work an example. Start with something fairly straightforward. I've got a 5 amp current source flowing up. Some arbitrary resistance R like so. A 3 amp source flowing down. A 1 amp source flowing up. And Dylan, could you tell me if you would prefer the resistor current to be flowing up or down? Down, okay. So this is going to be my resistor current IR, and Dylan has chosen that it is flowing down, okay. Let's see, Isaac, could you tell me which version of KCL you would prefer to do? Just 1, 2, or 3? KCL number 3, okay. And Sujita, could you tell me if we're going to apply it at the top node or the bottom node? Top node. Okay, so KCL number 3 at the top node. So currents that are leaving the top node are going to get plus signs, and currents that are entering the top node are going to get a minus sign. Those are the rules based on the choices that we've made, right? So KCL number 3, currents that are exiting are positive, applied at the top node. Okay. So the 5 amp source on the left, it is entering the top node, so it should get a minus sign. The current IR is leaving the top node, so it should get a plus sign. The 3 amps is leaving the top node, so it should get a plus sign. And the 1 amps is flowing into the top node, so it should get a minus sign. And we've now taken into account all of those currents, so we set them equal to 0. So that's the sum, or excuse me, the sum of the currents exiting the top node is equal to 0. We could rearrange this guy very easily and say that IR is going to be 5 amps minus 3 amps plus 1 amps. So 5 minus 3 is 2, 2 plus 1 is 3. So there is a net current of 3 amps flowing down through that resistor R. If we had done KCL number 1 or 2, or we had done any of these at the bottom node, we would still get the exact same results. So it literally doesn't matter which formulation you apply or which node you do it at. As long as you do it correctly, you're going to get the same result as everybody else. Okay. Let's work another quick example here. What we're ultimately trying to find in this guy is going to be the current flowing up through the 100 ohm resistor. As part of this analysis, we're going to wind up at least having to define the current flowing through the 25 ohm resistor so that we can apply KCL to this system. Okay, so let me backpedal just a smidge here. So in this particular circuit, where everything is connected in parallel, hopefully we can all see that. This is an example of a single node pair circuit. Okay, so that all of the elements are shared by a single pair of nodes. In this case, the top node and the bottom node. Sometimes you'll see it as everything is between the left node and the right. Okay. Anytime I had a single node pair circuit, my gut instinct is to apply Kirchhoff's current law to it. Okay. In order for us to apply Kirchhoff's current law to this system, we need every branch to have a current associated with it, right? Well, the 8 amp current source obviously has a current associated with it. The 100 ohm resistor, I've now defined the current I100 that we're trying to find, so that has a current associated with it. The 3 amp current source on the right-hand side has a current associated with it. So we're left with a 25 ohm resistor, okay? So we have to make an educated guess as to the direction of that current. Doesn't matter which particular direction we choose. So for the sake of being a jackass, I'm going to choose down so that it's in the opposite direction of I100, so that if and when we apply Ohm's law, we have to think about things because the directions are different on those currents. Okay. So I'm going to call this current right here I-25 direction down. Okay. So since we did KCL number 3 at the top node in our last example, we're going to do a different version of KCL at the bottom node for this one. Okay. So just for the hell of it, because I don't use it very often, let's do KCL number 2. So that means that currents that are entering the bottom node are going to get a plus sign, and currents that are exiting the bottom node are going to get a minus sign. Okay. I'm just going to work my way from left to right. So the 8 amp source is exiting, so it's going to get minus. I100, excuse me, is exiting, so it's going to get minus. I25 is entering, so it's going to get plus. And 3 amps is entering, so it's going to get plus. And I'm going to set this equal to 0. So we now have one equation with 2 unknowns. I think pretty obviously I could move the minus 8 amps and the plus 3 amps over to the right-hand side, get my constants on the same side. We'll do that in a little bit. But how am I going to come up with another equation here? Because if I apply another KCL, it's just going to give me this exact same equation. Doesn't matter where I apply it. I'm going to get literally this relationship in some form. Okay. So I need to use Ohm's law. Okay. And if I'm going to use Ohm's law, V is equal to I times R, then I need to assign a voltage. Well, all of these are in parallel, and a couple of minutes ago, we learned that when everything's in parallel, they share the same voltage drop, right? So I just get to choose to put the positive polarity on top or positive polarity on bottom. So somebody make that choice for me. Positive polarity on top, okay? So I'm going to say that this voltage, V, is for every single one of these elements, right? Because that voltage is defined between the top and bottom node, and all of those elements are connected between the top and bottom nodes. So down here, I'm going to write an Ohm's law equation for those two resistor currents, right? So let's start with I100. How would I express that current I100 in terms of that common voltage V? So V over 100 ohms is somewhere to start, but that's technically incorrect. What do you think needs to be done to fix it? Negative sign. So it needs a negative sign because that current I100 is flowing out of the positive polarity terminal. So it started flowing in here into the minus terminal, flows through the 100 ohm resistor, and then flows out the top. So since it's flowing into the negative polarity terminal, Ohm's law needs a minus sign. How would I express the current I25 in terms of that voltage?
V over 25 ohms.
V over 25. Do I need to add a minus sign this time? I do not, because the current is flowing into the positive polarity terminal. Okay. And so now I can simply substitute those relationships into my KCL at number 2 equation thing up here. So negative I100 is negative V over 100 ohms, plus I25 is just V over 25 ohms, is equal to, I'm going to move the 8 amps over here. I'm going to move the 3 amps over here. So that's going to look like V times a factor of 1 over 100 ohms plus 1 over 25 ohms is equal to 5 amps. So I can find out what V is. So 5 divided by 1 over 100 plus 1 over 25 gives me 100 volts. And then substituting that value into this expression, I get negative 100 volts over 100 ohms is equal to negative 1 amp. See some confused looks. By all means, tell me what part of my algebra you weren't catching. Okay. You weren't the only one with a confused look, by the way. Yes.
So I100 is negative, and then flowed into the negative term first.
I100 is negative because we arbitrarily chose the wrong direction. So in real is like negative 1 amp up is the same as 1 amp down. So if we think about this thing intuitively, okay, so using intuition, I would say that 8 amps is larger than 3 amps. Well, that's not intuition, that's just a fact actually, right? So 8 amps is larger than 3 amps. So 8 amps is going to be the dominant current source in the system. So I would expect this current source, let me use a color I haven't used already, right? So it's flowing here. And then it's going to have an opportunity to split up, right? When it sees those resistive paths. So intuitively, it's going to want to split and flow down through them. Because I-100 was assigned in the opposite direction of that, we wound up getting a negative sign. So that's, in my opinion, a better way to think about that. Yeah. All right. So I think that is enough out of me for today. So you guys have an in-class assignment and all of that kind of stuff to do. If you have any questions about anything, I would be more than happy to help you all.